Oh, thank you. I don't know how to get, oh, there we go. Right, so we're gonna move now. We were talking about characters in general, right? And we were trying to see how we group organisms in terms of similarity. We talk about how important it is to score those traits and evaluate them before moving into this type of analysis, which is phylogenetic inference. A little bit of an overview of the section. We're gonna have a lecture. I have some planned like breaks, but if you have any questions, if you're like having a hard time following, please stop me. And I tend to talk very fast. So if I'm going too fast, do let me know. Then we're gonna have a break for more coffee. And then the idea is that we're gonna work on the tutorial here, right? There are different levels of experience. I know that some people may have done stuff in RevBase. So the idea is that once you're working in the tutorial, you can focus on whatever you want to learn, like whether it is the syntax or whether it is the model itself. In terms of the lecture, so I'm going to start by talking about how a Bayesian does phylogenetic inference. We have different types of inference. So I'm going to touch on that briefly. Then we're going to jump into divergence time estimation. There are two types of divergence dating. So I'm going to compare to the other that is no dating. And then we're going to go through the model of Bayesian total evidence dating in RevBase. So that's going to be a lot of modeling vocabulary. Okay. Before I jump into the lecture itself, I just want to say a thank you note to my two mentors. So these are my mentors in terms of phylogenetics. And I also want to thank them for many of the slides that you're going to see today. So let's start by a practical introduction of Bayesian phylogenetic inference, right? There is a lot of theory behind this, but I'm going to focus on what you as a practitioner need to understand in order to implement your models. So it's practice-oriented. Because you're here, I feel like I don't need to spend that much time convincing you that phylogeny, right? But the problem with phylogenies is that they're really hard to estimate. And why are they hard to estimate? Has to do with the fact that as we increase the number of tips, so the number of species or terminals that I'm studying, the number of possible traits just like goes exponentially up, right? So if I want to pick one phylogeny among all those, I have to explore that huge amount of trees. Historically, there have been three approaches that we use to estimate phylogenies. I'm going to quickly compare them just because you may be familiar with one over the other. So the first one is parsimony. When we do inference in parsimony, we assume that there's one tree that is the best tree, and we're going to select that tree based on one optimality criterion. And in this case, who can tell me what's the optimality criterion in parsimony? Minimum number of changes, right? So that's the criterion I'm going to use to select. So basically what I do is to explore the tree space and select the tree that has the least number of changes. But that's as far as I'm going to go on parsimony, because we're going to use a different approach, which is shared by maximum likelihood and Bayesian. And the fact is that these two methods take a model approach. So the first assumption we're making when we do this type of model-based inference is that we believe that we can model the process of evolution, right? Which some people may disagree with. But let's assume that we think we can model the process of evolution. The way we're going to do this is we're going to estimate parameter values that are related to our evolution model based on the likelihood of the data. Who can tell me what do you think is a likelihood? Is the likelihood? Yeah, exactly. So the probability of the data given a model. So I have some parameters and I compare with my data that I have observed and I have a probability, okay? We're gonna talk a little bit about that later, but basically these two approaches share the fact that we use parameters and we use likelihoods. What is the difference between the maximum likelihood approach and the Bayesian approach? Practically, it means the difference is that we use posterior probabilities that rather than likelihoods in maximum likelihood, right? And what is a posterior probability? It's a likelihood modified by a prior, okay? So we have two things that our probabilities depend on. Who has heard about priors? All of you. What do you think about priors? It's a distribution that you specify usually. What does that distribution mean? Yeah, yeah, exactly. So we use priors to specify our previous or starting point ideas of how evolution or a particular parameter works, right? Some people are uncomfortable with priors, but we're going to try to demystify a little bit what a prior is and how we specify them, okay? Some practical advantages of using the Bayesian approach over the maximum likelihood are that Bayesian analysis come with a measure of uncertainty by themselves, right? For those of you that have used IQ3, how do you get a value of uncertainty on your trees? You have to compute something. Point estimate, so you have one phylogeny, and then you use that phylogeny and change the data to get bootstrap values, right? Bayesian inference comes with its own values because we don't estimate one tree, we estimate a distribution of trees, okay? So those measures of uncertainty are what we call posterior probabilities, credible intervals in terms of like the age, okay? Another practical advantage is the fact that we can easily build hierarchical models because the Bayes theorem works in a way in which you can build complex models really straightforward, at least theoretically, okay? So the advantage of hierarchical models are that we can use different sources of information, which is relevant for and morphology, right? And similarly, we can include more complex models because we need to model each of these data with different models. However, it sounds really good, but there's some cost associated with it. And I hope after this talk, I'll convince you that this cost is worth the effort, okay? But some of the cost of approaching in general with models is that our results are sensitive to the model that we assume, right? So there are like two steps that sometimes are hard to separate when we're specifying a model. So when I say specify a model, I mean, I'm going to tell RefBase how I think evolution works, right? So I'm going to tell the program what is the relationship between their diversity, right? So all of those are assumptions. I'm not testing them by running an analysis, a classical inference analysis, okay? So we have to take a lot of time to think about our model. And one of the things I want you to remember at the end of this talk is that we usually spend a lot of time in collecting data and getting like nice traits, well coded, but we don't spend that much time on thinking about our model. And we should really do it because our results depend on that. And the other cost of using Bayesian inference is that we need to specify a prior. Now, I don't know if this is something that you have heard before, but sometimes people think that priors are bad because they're going to bias our results, which may be true. But the reality is that we don't live in a world where we don't know anything. There's a lot of knowledge around. And those things that we already know and putting them in the model in a specified, explicit way, rather than assuming things, right? So I don't think priors are bad, as you can tell. The last thing is that we have to we have to use an algorithm, the MCMC, that can take a lot of time, and it doesn't work as easily as we may want, okay? But that's a problem with any kind of analysis at the end. Okay, how are we doing so far? Thumbs up, thumbs down, okay. So now we're gonna try to put ourselves in the shoes of a Bayesian and try to see how they see the world, because that's gonna help us understand how we specify models, okay? So if you're a Bayesian, you will think that the parameters, just put something that you care about. So put a tree. A tree is a parameter, right? Diversification rate is a parameter. A substitution rate is a parameter, right? And all those parameters are random variables. Why is it important that they are random variables? Because they have a probability distribution. If a variable has a probability distribution, then I can use the rules of probability to estimate those random variables. So this is sort of like a theoretical assumption. I'm assuming that I can estimate all those parameters that I am interested in. Does that make sense? Okay. The second thing that a Bayesian would think is that the best way to estimate those parameters is by using the Bayes theorem, okay? Which in practical terms means, again, that we need to use formulas. Hope I don't lose you here. I made this pretty accessible to formula panic. So this is the Bayes theorem. Let's check what this means in the real world. So the X denotes our data. So what kind of data do we use in phylogenetic inference? What would be my data? Alignments. What else? We just talked about that all morning. Character matrices, right? So those would be those two types of data we use, right? We also use fossils. Fossils are data, okay? And then theta denotes parameters. So what would be one parameter that you guys would be interested? A tree is a parameter, perfect. Your branch length is another parameter. Substitution rate, and we can keep going, right? So all those are parameters that depend on my data. What you have to remember about Bayesian inference is that we have basically 4 terms interacting there, right? So we have the term on the right, it's the prior. So the yellow one is the prior. So we could think of a prior as I don't know why my pointer is not working, sorry. Oh, there we go. Sorry, online people, I hope you can follow. I cannot point on the slides, but basically we have a prior distribution that we can specify as a line, for example. That would be a uniform prior. And then we have another term, the prior is multiplied by the likelihood. So we already talked about the likelihood, what it is, right? It's the probability of the data given my parameter. Could be represented by this yellow curve here. Oh, sorry, no. The likelihood, I would take it from my data, and then I would update it and would get the posterior probability. So the posterior probability is a function of likelihood and prior. So I start with a prior belief. I see my data, and I update my prior belief in what we call the posterior. Does that make sense? In practical terms, I may have an idea of what the relationships are in a group. I could use that as prior information, putting constraints or whatnot. Then I could take my data, morphology and molecular, calculate the likelihood, and get a posterior probability. So my new tree. Now with my extra data, what do I think now? Okay. Another thing that is noteworthy here is the fact, as I mentioned, that we care about the distribution, not only we can have a credible interval. So a measure of how confident can I be about that point estimate. But the real issue with Bayesian inference is that we have this term, probability of data, otherwise called the marginal likelihood, which is really hard to estimate. Okay, it's really hard to estimate because as you can see these awful formulas down here, there are a lot of integrals, which are really hard to get, right? But nothing is lost here. Don't worry. This is where we can use MCMC. MCMC comes to save us, and we're not going to estimate the marginal likelihood. We're going to use MCMC to estimate the posterior distribution without needing the maximum likelihood, the marginal likelihood. Okay. So I think it will be similar. So you basically, what you're doing when you're using MCMC, I don't want to go into a lot of details, but basically you're taking two values of a parameter. So you're taking two different values for your parameter here. And then you're calculating a radio. So the probability of one value divided by the probability of another value. And you cannot know exactly the marginal likelihood, but they cancel out because I'm dividing. So my marginal likelihood cancels out. And I don't know how much one parameter is better than the other, but I know that it's better or is worse. So that's how it works. Does that make sense? Yeah. And that's exactly what I'm going to get right. So let's talk a little bit about it. Oh, go ahead.
Even though they are assumptions, they are also parameters and they are estimated also, right?
The priors are not estimated, the priors are assumed. So for example, I can think, oh, sorry, online, there was a question about whether priors are or not estimated. And the answer is not. I assume priors. So let's say, I think this lineage diversifies at a rate, or even better, I don't know what rate this lineage diversifies, right? But I know that a sensitive value, something that would make sense would be between 0 and 1, for example. Then I would put a flat prior, as I show there, like a flat line. So I have no idea where between this 0.0 and 1 those values are possible, right? So I would put a flat prior and let the data update my prior belief and give me a posterior distribution, which is the yellow one. Does that make sense? All right, MCMC. So let's talk a little bit about this algorithm, because when you're running a Bayesian analysis, you have to set up an MCMC, right? So MCMC is an algorithm that draws samples from the posterior distribution, so the left side of our equation that I just showed, without having to compute the marginal likelihood, because we were talking that that's really hard to compute. So how does it work? Let's start with a very basic example. Let's imagine that we have two parameters. We have θ1 and θ2. And you can put whatever tree and rate or two rates just think about something that you care about. So the way this algorithm works is that we initialize the chain, so the MCMC chain, in that little black dot down there, right? So that little black dot will have a value in the horizontal axis, so a value for the parameter 1, and then another value for the parameter 2, right? And I start randomly. So the next step would be to choose which parameter I'm gonna move, right? So I could either pick my parameter 1 on the horizontal axis or my parameter 2. In this case, let's say the algorithm chose parameter 1. So I'm gonna propose a new value on this x-axis, which will be the red dot, right? So I propose one change. Get the acceptance probability. So I'm gonna choose whether or not I accept this parameter. And let's not worry about the formula. Just, I'm gonna tell you that this is a magical formula that if the probability of the red dot is greater, I'm gonna always accept the red dot. If the probability of the red dot is not greater, there's still a chance that I accept it, right? Why do I want to accept changes even if they're not always better? Do you have any idea? That's awesome. Yeah, exactly. So we had someone saying that we want to explore parameters that have worse posterior probability, just so we are able to explore the full parameter space. And that's something we wanted, okay? Because the posterior probability, okay? So yeah, I either accept or reject the proposal. In this case, we rejected it. And then I go back and do the same, right? I go back to number 2, and then I choose another parameter. In this case, now it's the vertical parameter, and I keep moving, right? And we repeat this for many and many and many and many generations, right? So if I repeat this for a long time, or like long enough, I'm gonna get a sample or an idea of the posterior distribution. Does that make sense? And again, I care about the posterior distribution, not only one point estimate. Because at the end, I wanna have a distribution, right? For the parameter 1, and what are the values for the parameter 2. Why is this important? Because then remember that my algorithm is working in a way that I explore the space parameter in proportion of how probable the parameter value is. So the more I explore a value is because that value is more likely to be true, right? Great. So that's what we do when we run an analysis, right? When we run an MCMC, that is what we're doing. We're exploring usually not one, but several parameters in phylogenetics. Yes, question.
How is it constrained? It's obviously constrained. Somehow that's why you have a distribution, not like random spread of stuff.
Oh, sorry. So there was a question about these distributions that we find at the end. They're obviously constrained to some values, so it doesn't go to infinite values in either direction, right? And the question was how it is constrained, and the answer is by a lot of things. The first one is it's constrained by your prior, by what I believe at the beginning. If I set my analysis saying these values are not possible, so let's think about extinction rate, right? I have an extant clade, so I have species nowadays. I cannot have relative extinction rates higher than 1, because that would mean that every single species that appears gets extinct, right? And because I'm seeing in my data that this group is alive, those values don't make sense, right? So I could specify a prior that would not allow values higher than 1, for example. You could take, and this is the hard part, we have to make decisions when we're specifying this. Because I could say, okay, I'm gonna let my analysis explore values that, even if I think those values are not real. And then that's when the data would come in, right? Because this posterior distribution depends on the prior and on the likelihood. Come back to the formula, likelihood, prior. So my prior will constrain it, but my data will also constrain it. If my data says that value is not realistic, I'm not going to explore that space. Does that make sense? Sorry, I can't hear.
So you're simulating a data set based on your priors, and so you're simulating the data points based on your original data and use that simulator itself to substitute for like standing or substitute.
I didn't quite follow, but so basically what you're doing is you're taking a prior, your prior idea, right? And then you have some data. I take that data through the likelihood function and update my prior belief through this likelihood function to get my posterior, which is very straightforward. Is I have some idea, I see some data, I have a new idea, right? The issue is that I have the marginal likelihoods. Yeah. So the issue is that I have the marginal probabilities that are really hard to get. And I avoid that by using MCMC. So that's like the basic idea, okay? You usually don't. It's an algorithm that is set up. In most of the analysis, the algorithm of the acceptance probability is set up in a way that it will always accept better parameter values with higher posterior probability, and sometimes values that are less probable, right? Okay, so we can run our MCMC by using any of these programs that you may be familiar with, right? So that's what they are doing. But we still need to specify our model. Oh, wait, I went too fast. Sorry, we can run it here. But then we may ask ourselves, how do we know if our MCMC is working or not? Basically, is it exploring the space or not? And I'm just going to give you a couple or ideas of how we do that. And at the end of today, you're going to do that using this software called Tracer. So I used RefBase to get my MCMC, and then I got some results, right? So you can see there my files. I have some trees, but I also have this .log file, which is storing all my values that I explored, right? So that's where I'm going to get the distribution from. Then I can visualize that in this program called Tracer. What do I need to check? I need to check for two things. So the first, well, Tracer is going to look something like this for the people that are not familiar. So that's like the Tracer screen. On the left, I have all my parameters, right? So you can see there are a bunch. And then I can see the trace, which is this plot. So in that plot, we can see the parameter space being explored in terms of, and in the y-axis, I have the values for my parameter. So that is a bad plot. I don't want to see that. I would say the way we would say that is that it hasn't converged. So it hasn't reached a point where it stabilizes. It kind of does up here, but like not really. So, but what do we want? We want something like this. So what this means is that I started near the bottom of the graph, and then I started exploring the parameter space and eventually got to a point, so like up there where the green, how do I describe this? Where the values are moving in the same, along the same value, so on top of the screen, we can see that is converging. So it's converging around one value. It's exploring the same space. Does that make sense? Right? But what would be even better? It would be even better if I run not one chain, but multiple chains. So here I'm running the green chain and the yellow chain, and they are both converging along the same parameter, right? Because why is this good? Like, why do I want different chains to get to the same result? What am I avoiding by checking that this gets to the same result? Exactly. So I am avoiding getting stuck in local optima for my parameter values, right? So when we get that, we call that convergence. The other thing that I could visually, and I should visually check, is the mixing of the chain. So mixing refers to exploring effectively the parameter space, right? So if I have a chain, kind of on top, but it's not really moving as fast as I would like, that's, if I see something like that, it will eventually get to a point where it looks fine, but it will take so many generations, so a lot of computational power. What I want is something like that. I want quick changes in my parameter values, exploring all the space, right? And you can see that this mixture reflects on the ESS value, which is basically the effective sample size. So tracer is really nice in that it colors. So if it's red, it's bad. If it's black, it's mixing at least, okay? So we joke in the lab and we say that those are fuzzy caterpillars. We want fuzzy caterpillars, right? I don't know why I put this. Practical advantages that we get, and it's not that hard to get to this point. But I thought that this was going to be like a natural break point in case you have any questions.